Family, welcome to the machine design class where now we will be discussing the deflections. So, tune in for fun time. Okay, just to begin this lecture off on a good note, what I just said to everyone was that we haven't really gotten into this class. The hard part of this class is the review part of this class. It's really understanding the fundamentals of what happened in mechanics of materials, what happened in statics, bringing all of that stuff together and figuring out what to do with it. The goal for this course is a design class. You can sit there and do math all day long in mechanics of materials and statics. You can do free body diagrams, you can throw them down like nothing. Okay, but if you can't apply this material, then it's kind of a waste of time. So we're going to be discussing a lot of this material. We're going to get heavy into this material. We're going to be doing a lot of examples. This is just a challenge. This is a challenging class because you have to remember a lot and you have to be able to use it, and it has to make sense in order for you to use it correctly. Okay? I will be able to know whether or not you're using that information correctly because it's going to show. If you can't design a component and you can't recall what we learned in statics and you can't recall what we learned in mechanics of materials, you're going to struggle in this class. You're going to have to spend some time reviewing that material in order to even do the homeworks. This is a high-level engineering class, and I do expect you to be professionals now. So, that said, the hardest part of this class still remains just recalling that material. I'm not going in great depth there because I do want you to spend time reviewing that material on your own. You will get swamped very quickly in this class if you don't. I am doing my absolute best to try to keep everybody up on par, but we're doing this in hybrid learning, which is not easy, and we're doing hybrid learning over the most difficult mechanical engineering class. You're going to take it down. So, all right, let's talk about deflections. The idea of deformations is actually very incredibly mathematical. The governing equations for this, if we go back to what we talked about even in mechanics of materials, the governing equations for this are really outlined by equations 410 through 414. Which I will write those on the board because I don't expect you to have those memorized. Okay? Q over EI. Well, this is going to be equal to your fourth derivative of, well, y over x. So if we have a beam that looks like this, maybe it's being loaded, looks like a macaroni noodle, and this is y and this is x. The slope of this beam at any location can be given by a derivative equation. Well, the fourth derivative of this relationship, the equation for this line defining the shape of that beam, the fourth equation is equal to the loading on that beam divided by the modulus of elasticity times the geometric moment of inertia. So, yes, that's gross. Okay, now step 2. You take the integral of that. V over EI is equal to the integral of that. That's a 3. Okay, you take the integral of that. M over EI. Okay, you take the integral of that. And this is equal to what's now, we're changing this up, and this is now theta is equal to dy dx. Now, what that means is theta is equal to the slope of that beam. And so if I want to know what the slope of this beam is, right here, that angle is theta. And that is an integral of this. So if I take integral of m over EI is equal to the integral of d squared y over dx squared. You take the integral of both sides. This ends up being theta. So theta is equal to m over EI, and you take the integral of it with respect to x. Okay, gross. The last equation then is that y is equal to f of x. This is just the shape of the beam. If we were to come up with an equation that dictates what the shape of this beam is, it is y. Okay? So the progression of how we get from here to here ultimately is the way that we calculate stresses in the system. Okay? So far we've been drawing out our shear force diagrams, we've been drawing out our bending moment diagrams. I've been doing that for a reason. Okay, if your bending moment diagram looks like this, guess what? The integral of this is going to be what that is going to be what the slope of the line looks like. And then the integral of that slope of the line is going to be what the shape of the beam is. So if you can do a second order integral over this equation, if you can get to the moment diagram, and you can get to the shear force diagram, and you can integrate this, get a moment diagram, integrate this twice, and you end up with the shape of the beam, you've done all the math you need to figure out what the shape actually looks like. Now the nice thing about this is that yes, this math is kind of gross. This isn't fun math. This isn't the kind of math, and I love math too, but doing integral after integral after integral after integral, it gets really tedious. But thankfully, this is once again why I love the end of this book. In Mechanics and Materials, I suggested that you actually use tables that have been developed online. These tables exist in the back of this book too. This is table A9. In this table, you'll see here's a beam that is loaded with a constant downward distributed load equal to W. It has two simple supports on both sides. Now this gives you what the shear force diagram looks like. It gives you what the bending moment diagram looks like. That's great. It then tells you what the equation is for the shape of that beam. That's the y equation right there. Tells you what the shear force, tells you what the bending moment. If you wanted to know what the angle of that beam looks like with time, you could either take the derivative of this equation, or you could take the integral of the moment equation. Either one works, as long as you divide it by the modulus of elasticity times I. Okay? So we have the ability to use the pre-existing equations to solve all of these. Now that said, it does make, you still have to do math. You just don't have to do 4 integrals of math. And in some points, you do have to go all the way back to this theory, and you have to derive the whole thing yourself. I hope you never have to do that. Thankfully, you have solid modeling software such as SolidWorks. A lot of companies will now trust that modeling software over hand calculations. It's very easy to drop a minus sign in your mathematical calculations. It's a lot harder for SolidWorks to do it, or another finite element analysis software like ANSYS or LS-DYNA. These other softwares that companies will rely heavily on to calculate their deformations. And they can plot out node locations, they can plot out the shape of how this is changing, and they can do it, and they won't even trust the hand calculations as much because maybe they have a varying shape. Maybe the shape isn't nice. So when we're going to cover deformations in this class, a lot of the purpose for me doing so is because you need to understand the material. Deformations are something that are very valuable to understand. The math behind it gets a little gross, but if you know how to use the pre-existing tools to figure out those deformation formulas, or you know how to just derive them yourself even, you will be in an excellent place as far as an engineer goes. We could spend an entire semester deriving equations, practicing this over and over again, practicing how to go from here to there. We can, and it's not as much fun as just going back to the book, pulling out the formula and saying, what's this one? So what we're going to go ahead and do is I'm going to do an example using problem number, well, I guess table 7 inside of table A9. We're going to use the one that I just showed you, that I used as an example, and we're going to do an example off of that. So let's say what I have is I have a, oh, maybe it's just a structural beam. Okay, and that beam looks like this. Okay, and we'll say that maybe the beam shape is, you know what? Let's get funky. This is an I-beam. Okay. Let me look up a quick I-beam shape we can use. Doop-a-doop boop. So I'm looking up W flange I-beams. Going to the engineering toolbox, which is a nice resource. Let me quick share my screen with you. Boop. So now you can see the board too. I just went to engineeringtoolbox.com. It says a lot of information. Really, you can just look up W flange beams or I-beams or I-beam shapes, and from that you can get a lot of information on what they are. I'm going to go here because this is it's a nice resource that's been put together, has everything that you would need as an engineer. Let's say I don't want a thick one. Let's say we're going to do a W 12 by 14. It's got a 12-inch distance and it's 14 pounds per foot. Here, this gives you the dimensions, W and H. It gives you flange thickness, web thickness. The web is this piece, the flange is this piece. So this is the TF and this is the TW. So if we're going to, where is it? Yep, W 12 by 14. Then we'll want to know this information here. Okay, so it's about 12 inches. It ends up being 11.91 inches tall. It's about 3.97 inches wide. If I were to draw this shape, it would look a bit like this, where this is 11.91 inches and this is 3.97 inches. Yeah, nice. I'm going to scroll back up and remember what I'm looking for here. Here's your sectional area, pound per square foot. Moment of inertia in the x direction. Because we're going to be loading it, across the x direction. That's really the moment of inertia that we're looking for. You'll notice that the x directional moment of inertia is more than 10 times what the y moment of inertia is. It's the way that the beam is intended to handle. It's intended to flex so that the beam bends in this direction and it carries that bending stress on the top and the bottom here. If we were to turn this on its side and load it in the same way, it'd be carrying the maximum bending stresses at these 4 locations, and that's called the weak stress location for this beam. It's not as strong in bending that way. So yes, putting it straight up and down like this, that does give us an I-beam. what we'll do is we will go ahead and load this I-beam then with a certain load W. And what we'll say is we'll make this be 10 feet long or 120 inches. Okay, we're gonna have W be, let's say it's like a floor. We'll have it be, you know what, we'll do 100 pounds per foot. 100 pounds per foot. Okay, so a total weight of 12,000 pounds that's being carried on this W12 by 14. Okay, so then we have our two forces up here. This is going to be 6,000 pounds. This is going to be 6,000 pounds. Okay. Awesome. That's what we need to know. Now I've got W. If I look at my book, I've got W is equal to 100 pounds per foot, or, well, okay, that's pounds per inch. My apologies. So about 12 times higher than what I was expecting, but whatever. I got L is equal to 120 inches. I have IX, and this is going to be equal to, I'm going to go ahead and scroll down again. IX is equal to 88.6 inches to the fourth. Okay, we need an E value. Let's say we're going to make this out of steel. So what is the modulus of elasticity of steel? Okay, and usually it's, if you're dealing with structural steel, it's about 200. Just pop this up. Some people will always say it's 200 gigapascals, which is the equivalent of about 400. Well, no, sorry, which is the equivalent of something else. I'm looking for. No, we can easily just do that conversion. Let's say it's 200. We're using A36 structural steel, which is what a lot of I-beams is made out of. So 200 GPa to PSI, and that is 2.9 times 10 to the 7th, or we have E is equal to 29 MPSI, or mega pounds per square inch. Great, now I think we have everything we need to know. Switch back to the board. Yeah, sorry about that, Tyler. I was trying to show you what I was doing on the computer. But these are the values that we have. Okay, we know what W is, we know what L is, we know what I is, we know what E is, and yeah, there we go. Now, what we're going to go ahead and say is, what is the maximum Y deflection? Now, the book gives us an equation. Again, I'll hold this up for everyone who wants to read a book through YouTube video. It gives us the Y equation right there. It also shows us what the bending moment looks like, shows us what the shear force diagram looks like. We have everything we need right here. It's nice and already been calculated for us. So Y max is equal to 5 WL to the fourth. I'll draw my L a little nicer. Divided by 384 EI. Okay, so we'll multiply those two together. Assuming I can find my calculator, which I put my book on top of. And then we have, let's see, E times I is 29 million times 88.6 times 384, and that is the bottom value. What we have here is this is equal to 5 times 100 pounds per inch times 120 to the 4th power divided by 9.8665 times 10 to the 11th. Big numbers here. So 500 times 120 to the 4th power divided by 384 times 29 times 8.6. And what this ends up equaling is 0.107 inches. Usually you will get deformations that are even less than 0.1 inch. You should. If you're getting massive deformations out of your system, and your system is only a foot long, you're doing something wrong. And that's really the issue with deriving a lot of these equations is it's not hard to do an integral. It's hard to remember to carry the numbers so that you don't end up suddenly getting something ridiculous. When I was in college, that happened to me a lot. And deriving these equations sucks. Sucks butt. And I don't want to do that. It's gross. It's not fun. But when you get the right number, you know. And here, we did all this math right. We plugged in everything right. We got our units for E correct. This is important because here I had to plug in E as 29 times 10 to the 6th, or 2.9 times 10 to the 7th. You have to get all of your units correct. Once you have all your units correct, you have to make sure all of your derivations are correct, and it just gets gross. So I will be expecting you to be able to use these tables, okay? You have to be able to do that. If you can't use the tables, you don't understand what's going on as far as deformations goes. Okay. Let's go ahead and talk about one more thing before we're done talking about deformations. And it's the idea of superposition. Okay, superposition is a concept we've talked about in a couple of other classes. The basic goal behind superposition is that when you have superposition, you are able to add behaviors of systems. Like if you have a system behaving one way over here, system behaving one way over here, you can add those two behaviors to get one behavior. What happens when both of these conditions are happening simultaneously. Okay, so if I have a beam and my beam is hanging over a ledge and I have something like this, okay, there are equations that you can find for calculating the deformation of this beam. Now, if we were to throw this on, suddenly we don't have the equations for this, particularly if now we also add a concentrated load, a distributed load, all of these. What we can do for superposition is we go ahead and we break this down into multiple systems, okay? So for system 1, we have something that looks like this. That's it. We find the deformations of the system. We can find what the Y values are over here for this overhang. Similarly, what we can do is we can take a system that looks like this, and we can find the deformations of this system. And we can find the Y locations here. If we add the Y value at any location from here and here together, we get the total Y value from these two loading conditions. Now we add one more point load at the end, well, then all we have to do is add what the Y value is from this system. So we take these three equations that we can find online. We can find the equations for deformation for these three. You take these three and add them together, and what you end up getting as a result is the total deformation. So y total is equal to y1, which is this one, plus y2, which is that one, plus y3. And this is y total where y is a function of x. So it changes. At every x location, though, if we're talking about the same x, y1x plus y2x plus y3x is equal to y total x. Now superposition doesn't always work perfectly. In the real world, superposition doesn't quite operate the same way because deformations here will cause the loading conditions here to change. You're no longer pushing vertically, etc., etc. So superposition, it has its applications, and it is something that you need to know, and it is something that you're going to need to know for these homework problems that I'm going to give you next week. But in real life, this is why finite element analysis software is more highly trusted anymore than just doing hand calculations, because quite frankly, what does it do? Also, you could take a system, you could load it, you could just get out there and measure it with measuring tape. That's the old school way of doing things, because it's impossible to say that there's a calculation error. The only problem you have is a measurement error. And if you have people who know how to use a tape measure, you don't have those measurement errors. So there are a number of ways to solve this that don't involve doing math, but I'm going to expect you to understand the math behind this. I'm going to expect you to also understand how to derive an equation. So we aren't really talking through there. The textbook does go through examples of how to derive those equations. I'm not going to read the textbook to you. I'm not going to do what my professor, I had a professor at college that did that to me. I'm not going to do that to you, okay? But I will expect you to understand deformations, and this will be difficult for you, and I expect you to ask questions to me. All right, I will see you in class this week on either Wednesday or Friday. Have a good rest.